In order to better understand friction, there's one case we kind of have to realize is occurring. You may have noticed from time to time if you've ever tried to move furniture, if you've ever tried to move any kind of or slide any kind of heavy object, you'll notice that initially you have to apply quite a large amount of force before that object will begin to move. However, once you get that object in motion, if we remember back to Newton's first law, an object at rest will want to remain at rest, so you'll have to apply a fairly large force, whereas an object in motion wants to remain in motion, and you may notice that you don't have to apply as much force once the object is moving in order to keep that object moving. If you ever want to just do a small experiment to detect this, walk into your living room or your bedroom maybe and take either a chair or a desk and try and move it, try and slide it across the rug. You'll notice a certain amount of force is required to get that piece of furniture into motion. However, once you have it moving, you can apply significantly less force than you needed to initially get that object moving. So we have two cases we're looking at. There's one where your object is not moving, and we call that case the static case. Static in physics is just one way of saying not moving, it's completely at rest. There's actually an entire field of, or an entire area of physics called statics, which is just the study of things that are not moving, balanced forces, things like that. The other case is not as straightforward, but when you have objects that are moving, that is known as kinetic or kinetics. So the static case, you have no movement. The kinetic case, you have movement. So static and kinetic are going to begin to be terms we use to talk about objects that are not moving and objects that are moving. So we have two cases, as we said, the static and the kinetic. This brings us to the title of this video, the coefficients of friction. In order to understand friction or to better be able to calculate it, we have to take into account what are known as these coefficients of friction. Before we do that, we should also talk a little bit about why these two cases are different. And if I magnify these two surfaces right here, the floor and the box itself, well, what you'll see is that nothing is perfectly flat. So we have this section, which would be the bottom of this box, and it's resting on the floor. And despite the fact that these both look fairly flat, and if we were to run our fingers over them, we'd feel very flat surfaces, under a microscope, you'll actually notice that nothing is perfectly flat. Now, when this is in the static case, these little ridges have really had enough time to really interlock with one another. Since there's no motion, they are deep within the crevices of one another, and if you try and push this object, you're really going to have to overcome all of these interactions between these two surfaces. So it takes a fairly large amount of force, depending on the object, in order to get this object to start moving. However, once you do have this object moving, these ridges don't necessarily have as much time to re-interlock. They actually wind up sliding over one another. So while there is still some friction, you'll notice that there's not as much time for this block to really fall down and interlock with these grooves. Instead, they just kind of slide over one another. One way I try and equate this is imagine you're on the beach and you really have a chance to dig your fingers into the sand. If someone were to try and pull you, they could, but they'd have to apply a fairly large amount of force. Whereas if you were moving over the top of the beach and then tried to dig your fingers in, it would be significantly harder because as you're moving, your fingers are not really given enough time to really push down into the sand. Instead, your fingers will drag more along the top, and while you will generate some resistance, not nearly as much had you been given the chance to really dig your fingers into that sand prior to being pulled. So this is where the difference between static and kinetic friction come into play. And we're going to start to take a look at how we can analyze these and how they can actually help us take a look at forces. The next thing to realize is there's a Greek symbol referred to as mu, and mu is the actual coefficient of friction. We have two of them. We have mu sub s, which is the coefficient of static friction, the frictional force which must be overcome to set an object in motion, and mu sub k, which is the coefficient of kinetic friction, which is very simply the amount of friction that is resisting the motion once the object is moving. Mu sub s will actually increase and increase. I apologize. The mu sub s will not increase. The static frictional force will increase as you pull an object. will resist that motion, but the static is the amount of friction that's acting on the object prior to movement. So if you have a table that's at rest in a living room, say, and you try and pull on that table, if you only pull the small amount of force, very small, you'll notice that table doesn't move. But since you're applying a force in one direction and the table's not moving, there must therefore be an equal and opposite force in the other direction. That is the static friction. As you increase your pull on that table, it may still not move, but that force of friction will be increasing right along with the force with which you are applying to the table. You're going to hit a certain threshold of force that you apply before that table begins to move. That exact moment, that is when you've overcome the static friction. And then the friction resisting your motion will be the kinetic friction, which we'll see is actually less. So static friction, friction you must overcome in order for this object to move from rest, and the kinetic friction, once that object is in motion, that is the frictional force that is resisting that change in motion. So it's the same concept here. They're both friction. The friction needed to set an object in motion, and the friction resisting an object that is in motion. That's the main difference between our two coefficients of friction. I think the easiest way to take a look at these and understand them is with examples. So we'll look at two quick examples right now. In our first example, we have a block that is at rest on a flat surface, and there is an applied force of 200 newtons that is being applied to the right. We are given that the static coefficient of friction is 0.32, and you'll notice if we go back, I'm sorry, I did not define these. If we take a look, the static coefficient of friction, it's actually just a ratio. I should have said this previously. Mu, or the coefficient of friction, it's just the ratio of the force of friction to the normal force. And it's actually the same equation for the kinetic coefficient of friction. It's the ratio of the frictional force. Apologize, that might be hard to see. The frictional force to the normal force. The difference is for the static coefficient of friction, it's the static frictional force, and for the kinetic coefficient of friction, it's the kinetic force. So the amount of friction statically that you must overcome to move the object, and the amount of friction kinetically that resists the object that is currently in motion. So we know that the static coefficient of friction, which is the ratio of the frictional force to the normal force, is 0.32. And we know that the kinetic coefficient of friction is 0.21. What they're asking us to find is that actual static force of friction and the actual kinetic force of friction. The actual force that resists any change in that object's motion from rest, and the actual force that resists the object's motion once it is moving. Lastly, they want to know what is the acceleration of this object based on everything that's occurring here. I believe I left out, I did, so I will add in here that this block actually has a mass of 50 kilograms. So we have a 50 kilogram mass, and this force is acting on it. So the first thing we should always do in any one of these problems is draw a free body diagram. So we draw a free body diagram. We know that the center of mass is where all of these forces act. We know that this object must have some kind of weight. We know that it's at rest on a flat table. Therefore, there must be some kind of normal force. We know that this object has an applied force of 200 newtons to the right. And since we're given there's a static and kinetic coefficient of friction, we cannot ignore friction. And we know that it will oppose the motion of this object. So we have some kind of force of friction acting left, an applied force acting right, a normal force acting up, and the force of weight acting down. Now we should be able to do some basic calculations. We know that the force of weight is going to be equal to the mass of the object times the acceleration due to gravity, which in this case is 50 times negative 9.81, which will give us negative 490.5 newtons. So that is the weight of the object acting down. We should be able to realize that since the acceleration in the y direction is 0, that means that our net force in the y direction must also be 0. And in order for our net force in the y to be 0, our weight and our normal force must be equal and opposite. So the normal force must be 490.5 newtons. Now we don't know what the frictional force is here, but if we want to look at the static friction force, or the friction that resists any change in this object's motion, basically the force that must be overcome in order to set this object into motion, we will use our static coefficient of friction. Now we know that the static coefficient of friction, if we go back, is equal to the static frictional force divided by the normal force. That should help us figure out what we're looking for right here. So we know in this case that our static coefficient of friction is 0.32. We know that's equal to the force of friction, static, over the normal force, which in this case is 490.5 newtons. With some basic algebra, we should be able to figure out that the static frictional force will be 490 times 0.32, which should give us 156.96 newtons. That is the static frictional force that must be applied in order to set this object in motion. That's a little bit hard to see. I will rewrite it down here, 156.96 newtons. So if I apply 150 newtons to this box, this will not move. If I don't apply 156.96 newtons, this block will remain exactly in place. Now that we know this, we realize since 200 newtons is applied, it's greater than 156.96. Therefore, it's greater than the required force to move this block, and this block will move as a result. It will actually accelerate. So now the question becomes, since we know it's in motion and we know it's accelerating because we've exceeded the amount of force required to set it into motion, to change it from rest or to change it from its static state, we now have to figure out what is that kinetic friction force? What is that frictional force that resists the object's motion now that we've proven that it's actually moving? Well, hopefully you're seeing now that we do the same setup. However, we use the kinetic coefficient of friction, which in this case is 0.21, and it's equal to the kinetic friction force divided by the normal force. So if we just use our other coefficient, which is 0.21, we set it equal to our kinetic frictional force divided by our normal force, we should be able to find that the force of friction once this object is actually moving is 103 newtons. So while it requires 157 roughly newtons to set this object in motion, once it's moving, we only have to apply 103 newtons or more in order to keep it moving. So if we take a look, we now have the amount of force required to set it in motion, the amount of force required to keep it in motion, and lastly, we want to know this acceleration. Well, there's a few things we can look at here. We now know that our force of friction, once it's moving, is 103 newtons, so we can set that to 103 newtons. We know already that the net force in the y direction is 0, therefore our acceleration in the y is 0. We also know that in the x we have 200 newtons to the right, 103 newtons to the left. So if we'd like to calculate our net force in the x direction, that will wind up giving us 200 newtons minus 103 newtons, which should give us 97 newtons to the right. If we use Newton's second law, we should realize that the net force in the x direction equals the mass times the acceleration in the x direction. It's just F equals ma applied only in the x direction. We know that the net force in the x direction is 97. We know that the mass is 50 kilograms, and we're looking for the acceleration. Now in this case, we should be able to look at this diagram and realize, based on this setup, it will only accelerate in the x. There's no way that this will accelerate up and down. There's no up and down force. So if we solve this, we should be able to find that the acceleration in the x direction is 1.94 meters per second squared. I found that by simply dividing 97 by 50. So the keys to take away from this example: if we're given the static coefficient of friction, we should be able to find the static frictional force, which is actually the amount of force that must be applied in order to overcome this object's inertia and set it into motion. Once it's moving, the kinetic coefficient of friction can be used to help us find the actual frictional force that resists that motion. And just be aware that no matter what type of problem, frictional, gravitational, no matter what problem we're looking at, Newton's second law, F equals ma, will always apply. Sometimes it will be in the x direction, as it is in this case. Sometimes it will be in the y direction. But at the end of the day, if you know the net force in any direction, and you know the object's mass, you will always be able to calculate the object's acceleration in that direction.